So what actually happens when artificial intelligence doesn't just, speed up medical research, but literally gains control over who gets cured? We hear so much about AI as this simple, super fast lab assistant, but what if that narrative is entirely missing the point? What if the real story here is fundamentally about the centralization of biological power?
Hey everyone, and welcome to The Explainer. I'm so excited to guide you through today's analysis. We're diving into a really fascinating strategy-level paper titled GPT Rosalind and the Biochemical Control Stack. We're going to unpack exactly how biological AI is changing the very fabric of life science. It's moving away from just being a simple research assistance problem and turning into a massive control, verification, and governance challenge. Let's break down how this actually works.
Here's our game plan for today. We'll start with the illusion of speed, introduce the new discovery converter, examine the biochemical control stack, and then explore two opposing outcome pathways. Finally, we'll tackle the biological class divide and wrap it all up with governing biological sovereignty.
All right, kicking things off with Section 1, the illusion of speed, and reevaluating Eroom's law.
We really need to debunk the hype right out of the gate. The popular idea out there is that a biological reasoning model, like the theoretical GPT Rosalind discussed in our source, is just a really fast scientific calculator. But the reality? It's much, much deeper. The central thesis of the paper hits the nail on the head. A specialized life science reasoning model is not merely a faster research assistant, it fundamentally changes the energy structure of biomedical discovery. The real shocker here isn't just the speed, it's about who actually controls the entire discovery loop.
To understand why this matters, we have to talk about Eroom's law. You might know it as the frustrating observation that drug discovery just gets more and more expensive over time, despite all our technological progress. But this paper brilliantly flips that idea on its head and frames it as an energy loss problem. Think of it like a leaky pipe. Drug discovery loses energy across 6 distinct layers. You've got search loss in vast chemical spaces, translation loss, which is basically when a drug miraculously cures a mouse but completely fails in a human trial, plus you have coordination loss across totally fragmented literature, alongside huge validation, regulatory, and capital losses. AI comes in and compresses these really slow parts, completely reorganizing the front end of discovery to plug up those leaks and reduce that lost energy.
Moving right along to Section 2, the new discovery converter, and changing the 5 levels of science.
Okay, so we're shifting away from seeing AI as just a handy tool inside the system to seeing it as the central engine of the system itself. Drug discovery is this long, continuous, horizontal chain, right? You move from biological data to synthesizing evidence, forming hypotheses, pruning candidates, doing wet lab validation, and finally, reaching patient access. Biological AI acts as a centralized converter. It takes all that fragmented data, compute, and institutional priorities and converts it directly into ranked scientific action. And here is the absolute core of the paper's argument. Whoever controls this converter automatically gains immense influence over what gets researched, what gets funded, what gets commercialized, and ultimately, who gets access.
The crucial takeaway is how the actual unit of scientific work is evolving. Think about the old workflow. It was all manual literature retrieval, totally blind candidate searching, and tedious protocol writing. But now, we're stepping into a completely new paradigm. We're looking at computational evidence synthesis, highly intelligent search space pruning, and direct experimental control. The technology is evolving from just general AI assistance into full-on vertical scientific infrastructure, and ultimately into actual biological governance. Put simply, computational reasoning is stepping in and replacing the old wet lab brute force.
Which brings us to Section 3, the Biochemical Control Stack, mapping the EP layers.
Now, if we're putting this incredibly powerful converter right in the middle of the life sciences, we desperately need a vertical control stack sitting right beneath it to ensure things stay safe and accountable. This is the full energetic paradigm, or EP, control stack detailed in the source. Now, quick but important caveat, we are only looking at the public conceptual architecture here. The paper doesn't disclose proprietary EP implementation details, hidden algorithms, or private formulas, and since those operational details are absent, we aren't going to try to guess them. But from the public framework, we see exactly what makes biological AI trustworthy. You need energy mapping to see where resources are going.
You need constraint discipline for safety. Things like evidence tracing stop AI hallucinations, and failure memory ensures we don't repeat toxic, expensive mistakes. You even have incentive diagnosis to track who is actually benefiting financially. The point here is that control isn't some pesky obstacle to innovation. It is literally the productive infrastructure required for science to safely survive contact with physical reality.
Let's look at Section 4, two opposing outcome pathways. Who captures the value? This brings us to a massive tension point in the whole narrative. We all know AI makes things more efficient, but here's the billion-dollar rhetorical question. When efficiency improves, where does that saved energy actually go? Does it reach patients in the form of cheaper drugs, or does it go straight into monopoly margins and proprietary pipelines? You see, efficiency doesn't automatically equal liberation. It usually just gets captured by whatever control structure is built around it. And this dynamic sets up what the paper cleverly calls an asymmetric return loop. Let's walk through it. Patients contribute their biological data through hospitals and clinical care, right? That collective public data fuels the AI model's capabilities. The model then churns out these incredibly valuable proprietary therapies. But then, those exact same patients are asked to pay sky-high prices for access to treatments that were literally made possible by their own extracted data. So the inputs come from the many, but the monetization? Well, that could be entirely controlled by the few.
So, impartial reporting here, this leads to two massive structural risks that the paper outlines. On one hand, we face an open danger. This is where completely unrestricted access to these AI models could enable reckless or malicious biological design with dangerously weak accountability. But on the other hand, we face closed capture. This is where we lock the models behind huge corporate walls in the name of safety, but in doing so, we risk concentrating the entire future of medicine inside a few corporate alliances, completely shutting out public universities and developing nations. The solution isn't maximum openness or maximum secrecy. It's going to require carefully controlled diffusion.
Section 5, the biological class divide. Labor, rare disease, and anti-aging. This shift brings some profound societal implications, and it starts with a major shock to labor. Scientific work is migrating. The past relied really heavily on wet labor. Routine literature synthesis, endless manual trial and error, and blind protocol drafting. But the future, it shifts human value upwards into what's called system design. The scarce, highly paid researcher of tomorrow isn't going to be running repetitive assays. They're going to be doing objective mechanism critique, designing decisive validation experiments, and governing the interface between what the AI outputs and what happens in the physical world.
And this has huge implications for things like rare diseases. In a beneficial conversion scenario, AI lowers the cost of discovery so dramatically that the long tail of rare diseases finally becomes economically reachable. That generates incredible public health value. But warning, in a captured conversion scenario, a company could just use the AI to cheaply generate hyper-narrow therapies and then aggressively lock every single one of them behind a patent. In that world, we don't get widespread public health value, we just get a landscape littered with a portfolio of tiny, fragmented monopolies.
But honestly, the deepest, most explosive warning in the paper relates to enhancement and anti-aging. This brings us to the biological class divide. This happens when extreme biological optimization is distributed purely through market power and wealth. Think about it. Once AI successfully models cellular repair and aging, the boundary between a therapy and an enhancement totally crumbles. If things like enhanced cognition and radically extended health span are only available to the highest bidder, inequality won't just be about the money in your bank account anymore. Class structure could become physically embodied. The upper tier could literally buy stronger bodies and more time.
Which leads us to our final act, Section 6, governing biological sovereignty and control as productive infrastructure.
The source paper perfectly summarizes this phase transition. Biological AI does not merely accelerate drug discovery, it rewires the discovery economy. It changes where search occurs, who owns the hypotheses, who has the power to validate them, who can afford access, who holds the patient records, and who ultimately benefits from the compression of all that failure. Remember that central theme? Whoever controls this discovery converter fundamentally gains control over what gets researched and funded. It is a total rewiring of biomedical energy flow.
So how do we pragmatically manage these massive structural risks? The paper outlines a layered EP governance model. We need strict scientific validation gates to separate real hypotheses from AI-generated fiction. We absolutely need biosecurity task boundaries to prevent harmful biological design.
We must implement real data rights accounting so patient records aren't just extracted without proper consent. And crucially, we need tiered access so public institutions and universities aren't locked out, paired with very firm pricing commitments. Finally, human accountability has to remain absolutely central for all clinical decisions.
Look, the promise here is absolutely staggering. We're talking faster cures, personalized medicine, and a real fighting chance at defeating rare diseases. But the structural dangers of monopoly and data extraction are equally immense. The real task in front of us right now is not to try and stop biological AI. The task is to govern the conversion, from data into knowledge, from knowledge into intervention, and from intervention into equitable access. We have to ensure that the power to repair life doesn't just become the power to own life. So I'll leave you with this. What kind of biological future are we actually building? Thanks so much for joining me on this explainer, and keep asking the big questions.